So, welcome back everyone. We are basically discussing functional group based strategies for a given target, and we are basically following 6 different guidelines, and last couple of lectures we talked about this guideline 4, which you said that there are several strategies where you need to use protection and deprotection. So, if you are having a some chemically labile functional group which needs to be protected, you do the protection with suitable protecting group and then do the FGI with the remaining functional groups, and then at the end of this synthetic strategy you just deblock or remove the protecting group. Now, we already said that if you are having a two equally reacting or equally reactive functional group, you can basically use a one equivalent of protecting reagent which will selectively protect one end or one particular functional group, and this is basically you can do a stoichiometric control. Now, there are situations where you might have a difficult scenario. If you remember the last week we talked about some molecule where you are having this situation. I have given a molecule where the stereocenter of this molecules were actually given, that this OH is basically 1,3 anti. So, these two OH are 1,3 anti and this molecule is basically enantiopure. Now, there are another isomer for this molecule or another stereoisomers, we will find that the structure is this. This molecule is anti, as I said, this is 1,3 syn or cis. Now, if you see the right hand side molecule will not be having chirality because it is having a mirror plane of symmetry sigma v, but this molecule is chiral, but this molecule we said is having a C2 axis of symmetry. Now, we explained that when you are trying to do the protection of this kind of compound, this kind of compounds are very good building blocks for synthesis of natural products or other molecules. Now, I said compound A and compound B. As a compound A, there are two OH, OH1, OH2, and compound B also there are two hydroxy groups. If you remember last week we said that if you have this kind of compound where you are having a C2 axis of symmetry, the OH group or the similar kind of functional groups will be homotopic. So, now I say these two OH groups are homotopic. Now, homotopic means they are basically equivalent, and for this group as they are related with the mirror plane of symmetry, this OH are now enantiotopic. Now, what implication this topicity or homotopic or enantiotopic will lead you for the protecting group chemistry. We will now demonstrate with this particular example. Now, say we will take this particular compound, the second compound which is having cis relationship with this 2 hydroxy group, and we say this molecule is having a sigma v. Now, what is it? We will be doing a one equivalent of protecting group. Now, in principle this protecting group can come here as well as can come here. So, let us first see that if the right hand side OH is protected you basically get this. Okay. And now, if left hand side is protected, you get this compound. Now, what you do? You basically put a mirror and then you see these two compounds are now enantiomer to each other. That is what I said, these two hydroxy groups are enantiotopic, and as these two groups are enantiotopic, selective protection of any of this group over the other will lead to enantiomer. Okay. So, compound A prime and compound A double prime are basically enantiomer to each other. Now, in those cases, if you are not careful about these particular aspects, if you do some protection of this static material, you will basically end up with 2 enantiomers. So, you need to be very careful, you need to be very careful. On the contrary, the other example which you have earlier expressed or explored, if you take this compound, this will be basically leading you only one compound. And in principle, if you have this Pg and this OH, these compounds are essentially equivalent, same. So, that is why always C2 symmetry, if your molecule is C2 symmetric, C2 symmetry has advantage or advantages over sigma b, and it happens that many times your starting material or your intermediate or your precursor having C2 symmetry. We will be discussing particular this strategical points when you talk about stereochemical strategies little bit latter part of our discussion. Now, in continuation with this protecting group chemistry, next we will try to figure it out how 1,3-diol of this kind of compounds can be selectively protected. Now, 1,3-diol we have already talked that these compounds you can be easily protect with the help of corresponding acetonite by making its acetonite derivative when you treat this compound with acetone or a 2,2-dimethoxypropane, which is basically ketal of acetone, you do a trans-ketalization reaction. It is fine, this already we have explored. Now, there are other ways you can protect this compound. You can do a simple protection of these compounds by making corresponding benzylidene acetal. The chemistry is basically similar. Instead of your acetone, you are now using a benzaldehyde as the main reagent, or that is called benzylidene acetal. Benzylidene acetal. Even you can take another aldehyde where R could be anything. If R is H, you get the benzylidene acetal. If R is O methoxy, you get the paramethoxy benzylidene acetal. Now, this acetal is a good protecting group, it is absolutely fine, no issue. But normally, as I said, the acetals are basically acid labile. I mean, if your reaction conditions are strongly acidic or even little bit acidic, the acetals tend to open it up. So, these acetals you can basically do some different protection by using, you take this acetal, I said pH, and then subject it to a reagent which we already talked, it is a DIBAL, diisobutyl aluminum hydride, which is basically a bulky reagent, bulky hydride source. Now, if you subject this acetal with the DIBAL, what is going to happen? DIBAL is basically a Lewis acid. So, you will find that initial stage this DIBAL will be, now we say that R equal to R prime, means these groups are equivalent. Okay. So, we will talk about this symmetrical acetal. Then we are saying that this Lewis acidic side of oxygen is going to coordinate with this DIBAL and this isobutyl, and you have a negative charge on this aluminum, fine. Okay. Now, as I said r equal to r prime, there is absolutely no issue. Sometimes it happen r and r are not equal, or there is a huge steric differences. If r is pretty bulky, then your initial coordination will take place this side. If r prime is pretty bulky, then initial coordination will take part in this side. We will have some example when you talk about a non-symmetrical acetal, how they are cleaved with or how they are treated with diball and what exactly happens. Now, once this initial coordination takes place, next basically this particular bond is kind of polarized, and you will find that it will open up in this way to give you a benzyl kind of cation. Now, as all of us know that benzyl cation is quite stable. So, benzyl cation will be generated here. If r equal to this phenyl, it could be simple benzene ring, or it could be paramethoxyphenyl. Now, this is a benzyl cation, which is basically stabilized by this phenyl ring resonance as well as this oxygen lone pair. Now, this hydride from this diball is now transferred, and now you see you are basically now getting a benzyl derivative of one of the alcohol. And now just simply clip this aluminum oxygen bond by some hydrolysis, and then you will end up with OBN. Now, this is basically a simple monoproduction of a 1,3-diol, but without using a base and sodium hydride. In principle, this reaction also you can do if you have this diol by using sodium hydride and one equivalent of benzyl bromide, which you earlier said that if you have a similar kind of functional group which are chemically equally reactive, you can do it. But actually, if the base is you are not using, you can also have do the same kind of protection by using a different reagent system. You make the benzylated acetal, and actually this kind of 1,3-diol, when these are not symmetrically substituted, you can basically protect them with the help of benzylated acetal or corresponding paramethoxybenzylated acetal, and then cleave the acetals in presence of hydride donor like bulky hydride donor diball, and you get the unsymmetrical opening, the mechanism which you have just now shown here. So, our next problem is basically based on that. The next problem which I am going to talk about, the target molecule which was given is having this structure. If you are doing a purely functional group based analysis, you see that this compound one end having a hydroxy, one end having allylic hydroxy. So, there are many hydroxy, free hydroxy are there in the target molecule. So, definitely if you are doing some FGI, this hydroxy group should not be free, The starting material which is also given to you is something like this, which was supplied to you, that this ethyl is there, and basically you are having a triple bond. So, if you now closely analyze this part of this molecule is exactly resemblance with this part. So, only thing is you need a 1 carbon extension here, which basically you can do by simple chemistry. You can generate this anion here and treat with formaldehyde, then you can reduce this double bond. So, now do the simple straightforward retro, and also you need to protect this hydroxy group as well as this hydroxy group. Now, we say that if you have a intermediate which is something like this, you will be having a very easy job to assemble the molecule. Now, what is this? This is basically closely related with the starting material, where in the starting material you are having a secondary hydroxy group is protected. Now, we take this compound. Now, this compound is basically what? This compound is having a primary hydroxy and a secondary hydroxy. So, is a 1, 2, 3. So, it is basically 1, 3 diol, 1, 3 diol, one is primary, one is secondary. Now, we will. So, initially we take the starting material, PMB group, how you can deprotect? Last class we talked about, you can just treat with DDQ, you basically come to this diol. Okay. Now, if you see this compound, we now reacted with paramethoxy benzaldehyde in presence of H plus. So, now you see this is oxygen, this is oxygen. So, basically you will be having this paramethoxy benzylidine acetal. So, now here you are having this ethyl group and then you are having this alkyne. Now, if you see the earlier one, this is basically a non-symmetrical acetal, okay, because this group is having a bulky group and this group is having only hydrogen. Now, if you subject this acetal, we will again write this acetal in the next page and then we will see how this acetal will react. Ethyl group is there. Now, we say this acetal will now, this is basically the OMe. This is now reacted with dibal. And this is a bulky reagent, this aluminum will tend to coordinate with this side or this side. Now, if you find it sterically, this side is too much congested, but this side is not. So, what will be happening? Your initial coordination will takes part in this site. Aluminum, your hydride is here and your isobutyl group is there. Now, this side coordination I said is sterically much more favorable. You can have another coordination on that side, which I am also writing for your better understanding. Aluminum, hydride, isobutyl. Now, you see this side is absolutely crowded because it is having a very bulky group. So, this is absolutely crowded, that is why this is the main product which will be formed, and as this is formed, now basically your similar kind of mechanism how these acetals are opened up. Once it opens up, you basically generate now this compound. The stereochemistry we did not mention, but it will be remain same. This part will be your OPMB, PMB is paramethoxybenzyl, and then your ethyl is here. So, this is the initial molecule which you can get after this acetal cleavage. You will not get this side, you will get this side because this acetal is a symmetrical, it is not symmetrically substituted, it is basically unsymmetrical. So, next your synthetic scheme, what is next you will be doing? You now see you will having a typical this, oh no, we are little bit wrong here, sorry, your acetal will be opened up on that side, your acetal will be opened up in CH2O, 1 minute, yeah, so we are basically here OCH2, yeah. So, you will be now getting this O, this OH ethyl, yeah, OPMB. So, this things you basically now got, and then what next is required? What next is required from you is you just do you have a triple bond compound. So, you subject it to a base, normally LDA is preferred, and you find that the triple bond will, the acidic hydrogen will be now given the acetylite, and this acetylite you can basically quench with formaldehyde, you can basically get this corresponding propagyl alcohol. Now, this propagyl alcohol, there is a two way, the final product which you have seen is basically having this E geometry. Now, this is a very important reaction. If you subject this propagyl alcohol with lithium aluminum hydride, you will basically end up with this E geometry of this particular double bond, and you just subject this propagyl alcohol with this aluminum thing. And the reaction is supposed to be takes place in favor of some of this cyclic Allen kind of intermediate, or you can write in a better way, just change this intermediate hydrogen. So, basically initially lithium aluminum hydride will transfer one hydrogen from here, and then this oxygen basically Lewis basic side, it will coordinate with this aluminum, and then we will be giving this cyclic aluminate ester. And now, this carbon aluminum bond, it will basically hydrolyzed, it will be hydrolyzed by whatever electrophile you can use. You can just use simple water, because you need two hydrogen. Now, see this hydrogen is already here, and so this carbon aluminum bond and this hydrogen are trans to each other. Now, this bond cleavage will takes place. If you do a aqueous workup, you basically end up with this allylic alcohol, where these hydrogens are E or trans to each other. So, the in principle the last reaction is also a very important reaction. If I give you a some retro something like this, that how you can make this molecule with a triple bond. So, you can basically start with this triple bond using a base, you generate a acetylite and react with formaldehyde, you get this propagylic alcohol. Now, this propagylic alcohol you react with lithium aluminum hydride to give you the E allylic alcohol, and this is a very simple and straightforward reaction which will solve your problem. So, this kind of functional group assembly and this kind of particular selective protection and reproduction of this acetal cleavage, which is the problem which we have just explained, gives you a nice demonstration that how this protection group can be easily created, and then you do the FGI, and finally this this protection groups needs to be deblocked. We are talking about another simple protection group which is abbreviated as MOM. MOM basically stands for this compound, methoxy methyl chloride, methoxy methyl chloride. It is basically a ether. You take the corresponding alcohol, react with this MOM chloride with a base. normally base which is preferred, DPA which is this structure, diisopropyl ethylamine, isopropyl ethylamine or hunic base. Now, get the corresponding mom ether. Mom ether are exceptionally stable in base, base stable, but they are very labile in acid. They are base stable, but they are acid labile. So, next one we will just discuss similar kind of problem where you can use this particular concept. I will say we will be having a structure something like this bicyclic ketone. And then I say you have to convert this compound is a mom and is a benzyl. Now, I said moms are usually labile in acid. So, if you see the other protecting group is a benzyl and you have a lactone. Now, lactone can be in principle clipped by acid, but you need a stronger acid condition. So, here if you use a very mild acidic condition like paratoluene sulfonic acid, you can be able to selectively clip this mom group, where the benzyl group will remain unaffected. Even if you are compounds having a mom group, let us say, then you are having a silicon containing group, any silicon containing group, then say you are having a benzyl or PMB containing group. Now, here you have to see whether these three groups are orthogonal to each other or not. Now, silicon can be easily clipped by fluoride source, other two groups won't be touched. Okay. Benzyl and PMB can be clipped by DDQ, other groups won't be affected. Benzyl and PMB both can be clipped by hydrogenolysis by simple hydrogen palladium charcoal, other two groups are not affected. Now, here if you are having a mom and TBS, or because TBS is also acid labile, mom is also acid labile. So, then there is a little bit difficulties, but in the Silyl group if you are having a TBDPS which is not acid labile, you can easily control the selective removal of mom in presence of TBDPS. So, this kind of orthogonal strategy you will find very interesting, and we will discuss those strategies little bit later in the next week. So, till then have a good time.